Hello and welcome to this video for Chemistry 20 following the Alberta curriculum. In this lesson we're going to start the gases unit. We're going to look at some of our definitions and properties of gases, and then we're going to get into our first relationship of the different properties of gases and our first law, which is a formula that we have. This unit is a lot of formulas. There's some theories involved that we'll talk about, but it's also a lot of math. So if you enjoy math, you should enjoy this unit. So first of all, what are some of the properties of gases? We have a lot of technologies that we use that imply or are available to us to use based on the different properties. So things like scuba equipment, hot air balloons, jackhammers, dealing with how gases are compressible, how they exert a lot of pressure, how when they heat up, they expand and become less dense and allow for things to rise. So these are some properties that we're going to talk about with gases. These are called macroscopic or visible properties. So the first one we'll look at is that, again, they're compressible. The reason they're compressible is because the particles are spread very far apart. When you look at the difference between solid, liquid, and gas, when you have solids, your particles are really close together. They're usually touching. They are vibrating and moving, but very, very slowly. When they're in their liquid phase, they are further apart and moving more freely. And when they're in their gas phase, they're super far apart, the particles, and they have almost no interactions between them. They're freely moving. So that's why gases are compressible, because there's all this space in between the particles. So we can add pressure. When we increase the pressure, that's going to decrease the volume. Now, the volume is not necessarily the amount of gas you have. The volume is the space that you have to move the particles around. So if I increase the pressure, that means the volume's going to shrink, and I'm going to have the same number of particles in there. If my volume shrinks, I still have those 4 particles. They're now just closer together. Okay, so that's what volume represents. When I'm talking about pressure here, we're talking about the external pressure applied on this gas, allowing it to compress. Gases also expand as you increase the temperature, because as you increase the temperature, which we'll talk when we get into, again, some of the different laws of the gases, their particles move more quickly. They have more kinetic energy. They want to spread apart. So when they collide more and spread apart more, that means, again, they're taking up a larger volume. The space that they're moving around in becomes larger. But what if the volume is confined? So meaning it's in a container like a gas cylinder, like a metal gas cylinder, or a pop bottle, or a tire, that the pressure at maximum cannot expand. What's going to happen is the pressure is going to increase. If the volume cannot expand because it's a confined space, the pressure instead increases, because as those particles are moving more quickly with more kinetic energy, they collide with the walls of the container more. And that's what pressure, internal pressure is. It's the collision with the walls of the container. Gases also have a low resistance to flow because, again, those particles are so far apart and those particles are so tiny, they can fit through really small openings. They have a really low viscosity, allowing them to escape easily. They have low densities, which means they float. They are miscible in a lot of different solvents, particularly water. We will talk about how temperature affects solubility later on in the unit, but generally speaking, we can dissolve them in different solvents. And they also do not take up their own shape or volume. They fill the shape of the container they're in. So that's what I was mentioning before. When I talk about the volume of a gas, it's not necessarily the amount of gas you have. It is what space is it allowed to move around in, because it fills the space of its container. Now, kinetic molecular theory, this here is a little bit of a better image than what I was trying to show, between the difference between a solid, liquid, and gas state. Gases, again, are a state of matter. Any substance can be in gas state. If it's molecular, you break the intermolecular forces to make it boil or evaporate, going from liquid to gas, okay? So there are some gases at room temperature that we're familiar with, like carbon dioxide and oxygen and things like that. But again, any substance can be a gas. It's just a state of matter where, again, its forces that were holding it in liquid phase have been overcome, allowing it to separate and move more freely apart from each other. So as I mentioned, when something's even in its solid phase, it still moves. We might not see it moving at the macroscopic level, but at the microscopic level, those particles are vibrating very slowly. They do eventually stop vibrating at a certain temperature called absolute zero, which we'll talk about in the next lesson, but otherwise they're generally moving. Now, when you go from solid, liquid to gas, you give more energy to the particles. They start moving more quickly and more freely. So we have something called the ideal gas, which is a hypothetical theory or properties of gases that we have, which our gases that our general conditions mostly follow. At the end of the unit, we'll talk about when they deviate from this hypothetical property, but for now, we're going to assume these are the properties of gases. They are moving in constant random motion in straight lines until they collide with the wall or another particle in the container. They're defined as point masses, which means they make up a mass but do not take up a volume. And the reason this is, if I have one tiny gas particle inside of my container, it's so tiny that the volume that it makes up in that container is essentially negligible. Okay, so the one particle being so tiny doesn't really take up a volume, but it does have a mass associated with it, and it does contribute to the mass of what's found inside that container. And we also assume that the only collisions happening are elastic, which means kinetic energy is conserved. There's a nice image here showing you the difference between elastic and inelastic collisions. So elastic collisions, thinking of a ball bouncing, it bounces forever, it never slows down. Inelastic would eventually slow down, and we know in real life things start to lose energy, but hypothetically speaking, with gases at the conditions that we have in our environment, generally speaking, they don't really interact or collide very often, so that means that they never really slow down. Eventually they could, but we're going to hypothesize and predict and say that generally they don't. They don't contribute to a volume, they don't slow down, and they move in random straight lines. So that gets us into our first law that we're going to talk about that looks at the relationship between pressure and volume. So let's start by talking about pressure. So first of all, let's talk about atmospheric pressure. Now, there are gas molecules that make up our atmosphere. They have a very small mass, but the Earth's gravitational pull holds them towards the surface of our planet, and that's what enables us to have an atmosphere that is good, right? Because it has the air, the oxygen, and the other gases that we need to survive. The pressure is defined as the force per unit area, and there's a lot of different ways that we can measure pressure, but the standard unit that we use in Chem 20 in the Alberta curriculum is kilopascals. We're going to talk about the different units and how to convert between them. Now, pressure is exerted in all directions to the same extent, and if I'm mentioning atmospheric pressure, I'm talking about the force from the atmosphere surrounding that object. So think of the object having a column of air above it and around it, okay? Now, what this means is that when you are at a higher altitude, so if I'm up here, there is less air above me, and I mean, I shouldn't just draw it above me. It is above me and around me, right? It's in all directions. But there's that column of air when you're up there versus when you're down here, you have, this is going to be hard to draw a straight line, but you have all of those gases in the column around you and above you, okay? So what that means is when you're higher up, there's less gases. The gases are also less compressed up there because there's less gases, okay? So thinking of the pressure of the gases is a lot lower than when you are further down, okay? So our standard pressure that we use assumes we're at sea level. And then everything above sea level. As you go up in altitude, the pressure goes down, okay? So how do we measure pressure? So as I mentioned, there's a few different ways of measuring it. It started with Pascal and Perrier that used a mercury barometer. So what is a mercury barometer? This is an image of it, but you can simplify it by thinking of, I have a bowl with mercury in it. Toxic, not something you want to use these days. Barometers use different materials now. And it has, let's say, an inverted test tube in it with little millimeter increments. Okay? When they were at sea level, there was so much pressure pushing on the mercury. I should have made that a different color, but let's make, even though mercury is red, let's make the mercury purple. There's so much pressure pushing on the mercury that it moves up into the tube, and it fills up the tube to a certain millimeter increment. Okay? And at sea level, they found that millimeter increment was 760 millimeters. So they called it millimeters of mercury as their standard units of pressure. Okay? This is at sea level. Now, when you move up in altitude, as we said, the pressure goes down. So what happens is that mercury, oops, I erased my test tube there. That mercury has less pressure being put on it, so it doesn't go up the cylinder or the test tube as high. It maybe only goes up to there. Okay, so at a higher level, maybe now it's only 680 millimeters of mercury at a higher altitude. Okay, so as we went up in altitude, there was less pressure, less atmospheric pressure, so the volume of mercury in the test tube went down, whereas before, when there was greater pressure, it went higher up in the test tube. Okay? So that's originally how barometers work. We still have barometers today, and when we do our lab in this unit, we'll be using a barometer to test the pressure of the room because it's going to affect the lab that we're doing. So millimeters of mercury is the first unit of measure to measure pressure that we'll talk about. We will also talk about pascals and kilopascals, mainly kilopascals. These again are our standard unit for Chem 20 in Alberta. We'll talk about atmospheres and bars as well. So the way that we do this is by memorizing the relationship between everything. Okay, so this is the first relationship. This is your standard atmospheric pressure. So saying again at sea level. At sea level, I have 760 millimeters of mercury. That's equivalent to 1 atmosphere and 101.325 kilopascals. Okay, we also have the bar, which is equivalent to 100 kilopascals. Less commonly used is the bar, but you might see it being used. Okay? This, for my students, is on your periodic table, your data booklet on the front, these relationships. But if not, this is something you would have to memorize. So in order to do a conversion, we're going to use unit analysis. You can set up a ratio, or you can use unit analysis, dimensional analysis, another way of saying it. Okay? So for example, I'm converting millimeters of mercury to kilopascals. So based on that relationship that we saw before, there is 760 millimeters of mercury in 101.325 kilopascals. Okay? Now, I am starting with 650 millimeters of mercury. And I want to convert it to kilopascals. Okay? So I'm going to take these two values. I'm going to put one on top and one on the bottom. Which one goes on top and which one goes on the bottom depends on the units that you're trying to convert to. I'm trying to convert to kilopascals. So I want my kilopascals to be on the top. My millimeters of mercury therefore have to be on the bottom, and this is where I say this is like a unit analysis type of question, because if we have millimeters of mercury on the top here and millimeters of mercury on the bottom, they're going to cancel. Okay, so I put my 101.325 kilopascals on the top and my 760 millimeters of mercury on the bottom. Again, whatever you want to solve for goes on the top, and the unit that you're trying to cancel needs to go on the bottom so that it cancels with the original units you start with. So what I'm going to be doing then is taking 760 millimeters of mercury, multiplying it by 101.325, and then dividing it by 760. Okay, that's the dimensional analysis way that you can do it. The other way you can do it is you can say, if I have 650 millimeters of mercury per X kilopascals, I don't know how many kilopascals that is, but I know that when I have 760 millimeters of mercury, there is 101.325 kilopascals. Okay, so I'm setting it up as two ratios here. What I put on the top on this side, I put on the top on that side. Okay, and now I rearrange and solve for X. So I would cross multiply to get 650 millimeters of mercury times 101.325 kilopascals. And that would equal 760 millimeters of mercury times X kilopascals. So if I want to solve for X, then I divide both sides by 760 millimeters of mercury. And notice how we get the same formula that we did when we did the dimensional analysis. Okay, so we get 650 times 101.325 divided by 760. So the fraction way some students might understand more, but it's a little bit more work. So if you understand the dimensional analysis, which is really important, when you get to university, some professors just teach chemistry with dimensional analysis. So understanding that your units that you're trying to cancel, if millimeters of mercury is on the top, it needs to also be on the bottom so that they cancel. Okay, so either way that you want to do this, I usually do the dimensional analysis way. I take 650 times 101.325, then I divide by 760, and we get an answer of 86.659 so on kilopascals. Okay, now if this is a question that I'm using in subsequent calculations, I do not round it. When you have intermediate steps in an overall calculation, you only round your final answer. Okay, but if this was a question, a standalone question, and it's asking you just to do this conversion, then I would look, I have 3 sig digs in this number, so I need 3 sig digs in my answer. Okay, I'm cutting off a 5, which is going to round the 6 up, so then my answer would be 86.7 kilopascals, my final rounded answer, if this is a standalone question. If it's used in subsequent calculations though, again, leave it completely unrounded and use that completely unrounded answer. Okay, let's look at another example for doing a conversion. Convert 2.5 atmospheres to kilopascals. So I know that 1 atmosphere is equivalent to 101.325 kilopascals. Again, this information, if I scroll back a little bit, is coming from this here. 1 atmosphere is 101.325 kilopascals. Okay. So if I'm going to do the dimensional analysis again. I have 2.50 atmospheres. I'm going to multiply it by, I want kilopascals on the top, so I do the 101.325 kilopascals. Again, the kilopascals needs to be on the top because that's what we're solving for. Whatever we're solving for needs to go on the top. And then the other one, the 1 atmosphere, also needs to go on the bottom because my atmospheres need to cancel, so I'm left with kilopascals. Now this again should make sense, right? Because what I'm saying is I'm taking 250, I'm multiplying by 101.325 kilopascals per 1 atmosphere. That's kind of what that's saying. Okay? So 2.5 times 101.325 divided by 1, of course we don't need to divide by 1 to get the answer. We get 253.31 so on kilopascals. And again, if this is used in subsequent calculations, I leave it unrounded. But if it's a standalone question, I have 3 sig digs in my question. So I want 3 sig digs in my answer. That doesn't cut off the decimal. So I don't need to put it in scientific notation. I just need to round it. I'm cutting off a 3, which doesn't round it up. So it's 253 kilopascals. I always put a box or a circle or a highlighter, a line, whatever you want to do under your final answer to make it easier for your teacher to see. Okay, so now that we know how to convert pressures, here's some practice questions. So if you want to pause the video and take a minute to give these a try. These are the answers, rounded again as if they were standalone questions. Okay? So let's now get into our first law, our first formula. In Chem 20, some teachers, again, like I said, might not teach them as formulas, but that's how I teach them, making it, I find, a little bit easier. When we look at a formula, it helps us to identify our variables and then know which variable to rearrange and solve for. So the first law and formula we'll talk about is called Boyle's law. So these laws are named after the scientists that studied them and came up with their relationships. So this came after the scientist Robert Boyle, who studied the relationship between pressure and volume at a constant temperature, and the amount of the gas is being kept constant. Okay? So again, volume is not the amount of gas you have. Volume is the size of the container that the gas is allowed to move around in. The amount would be measured in either moles or grams. Okay? So we want to look at the relationship between pressure and volume. So as we said before, the pressure, the internal pressure that a gas is producing is based on the collision of those molecules with the walls of the container. So what that means is if you were to reduce the volume of the container, the gas particles get closer and they start to collide more. So if they're colliding more, that means your pressure is increasing, because the pressure, again, is the collision with the molecules. I used to have this nice little image simulation, I guess I could call it, that would show you what this looks like, but I don't think it works anymore, so I'm going to have to skip that. But again, think of it like this. If I were to draw, now I think I messed up we will close the program. My whole PowerPoint's going to close. Okay, just give it a sec here. I guess I kind of froze my PowerPoint doing that. We will go back. By the way, this is my fur family. This is Ava and Chester and Marla. My whole PowerPoint just kind of shut down for me there. It's okay, we'll get it back. So looking again at the relationship between volume and pressure. So if we were to, just going to try to get me to save it again. Draw a diagram showing volume versus pressure. So here is a gas in a container that has this volume, okay? I'm going to take that container and cut the volume in half. I can do this by, let's say I have a syringe and there's a piston on this syringe, okay? And I'm allowing this gas, this is just my piston, my gas is not in there, I'm just showing you like the handle to a piston or the handle to a syringe, for example, okay? Let's say I have 6 particles of gas. 1, 2, 3, 4, 5, 6. So the amount of gas are these 6 particles. Now when they're in this space, they're going to be moving around and colliding with the walls of the container a certain amount. But if I give less space, 1, 2, 3, 4, 5, 6, notice how they are all closer together. When they're closer together, they're going to be moving with the same speed, notice, because they're at a constant temperature. Temperature is the speed or the kinetic energy of the particles. So they're going to be moving at the same temperature or the same speed, but they're going to collide with each other and the container more often because they're closer to each other and closer to the walls of the container. Okay? So as you, again, decrease the volume, there is an increase in pressure. Okay? This relationship where one goes down and the other goes up is known as an inverse relationship. So Boyle's law states that the volume of a gas varies inversely with the pressure at a constant temperature and constant mass or amount. Okay? Now, a real life example of this, when we breathe. When we inhale, what happens is we increase the volume of our chest cavity. So that's going to make the pressure inside of our chest go down, which means the pressure of the atmosphere, which is constant, is actually now higher. Even though it's constant, it's higher than what's inside of our lungs. And so oxygen and the gases we breathe in are going to go into our lungs because of that process, just because there's now a lower pressure system inside of our body than the atmospheric pressure outside. Now, when I exhale, I decrease the volume in my lungs, which means the pressure goes up. So the atmospheric pressure is now lower. And again, the air always moves from higher to lower pressure. Gases always move from higher to lower pressure. So when you exhale, the gas goes out because of that pressure differential. When you inhale, the gases go in. So expanding and contracting the chest cavity, is what allows the gases to move in and out. Another example of this is when you dive. When you dive, you go down in the water, the pressure of the water surrounding you increases, and that's going to make the gases in your body shrink, which can be dangerous, obviously. So that's why we use scuba gear to prevent that from happening. How does this graphically look? And you do need to know this for your unit test. For those in my class, there's a question that asks you to relate the different graphs to the different laws and theories. So when you're looking at a graph, whatever goes on the x is always the manipulated variable. And we're going to be talking about manipulated and responding variables in labs that we do in this course. But essentially, the manipulated is what you are changing or what change you're allowing or forcing to happen. The responding variable is what you measure in response to this. So let's say I'm taking, again, a gas in a syringe and I'm manipulating the volume that the gas can go in. Right? So I'm squeezing that, I am exerting external pressure, but I'm doing it to change the volume. And I want to see what the internal pressure relationship is as the gas when I change the volume. So if I increase the volume, which is what a graph shows as we read this way, the volume would be increasing. What should happen to the pressure? Because it's an inverse relationship, it should be going down. Okay? And actually, inverse relationships go down in essentially a curved line, not quite a straight line, it's more curved. But what you should notice again is that it's an inverse relationship, so when one goes up, the other goes down. So this leads us into our formula that I use for Boyle's law. P1V1 equals P2V2. Okay? Some teachers might also teach it as PIVI equals PFVF. So it just means essentially we have a set of conditions that are changing. Okay? I have initial conditions and final conditions, or conditions 1 and conditions 2. Okay? Now my pressure, again, it needs to be in kilopascals. So that's what I was saying, when you're doing your calculations for pressure, if it's in a different unit, you need to convert it into kilopascals to put it in this formula. You would use the unrounded answer. Your volumes need to be in liters. Now in this formula, technically, if your pressures were in different units, as long as they were in the same units, they would cancel out and the formula would work. Same with the volume. If they were both in milliliters, for example, they would cancel and work. But I like to teach my students the standard units because in some formulas, if you don't have it in the standard unit, it will not work. Okay? So it's easier just to always put things into their standard units. Now, again, if I go back to this formula, what you make the ones and twos don't matter. It's just if I make, so for example, we'll do an example and we'll talk about it, okay? It says a balloon is filled with 30 liters of helium at 100 kilopascals. Now, whether I make this V1 or V2 doesn't really make a difference. If I make it V1, then this has to be P1 because this is the pressure at that volume. If I made this V2, then this would have to be P2. Okay, so as long as they match each other, it doesn't really matter which you make the ones and the twos. But when I have a volume of 30 liters, it has a pressure of 100 kilopascals. Okay, so you could go and list your variables. V1 is 30 liters, P1 is 100 kilopascals. I label them in the question, so if you don't label them down here, it's okay, it depends on your teacher. It's saying what is the volume, so I want the new volume when the pressure is now, so if my new volume is P2, this is the pressure at that volume, okay? So my V2 is my unknown, and my P2 is 25.0 kilopascals. So the reason listing your variables is helpful because it lets you know which formula you're going to be using. You want to use the formula in this question that deals with volumes and pressures, and that's Boyle's law. Boyle's law is P1 V1 equals P2 V2. Okay? Now, you can either rearrange the formula first and then put your variables in, or you can put your variables in and then rearrange. I usually put my variables in first and then rearrange. Okay? So my P1 was 100 kilopascals, and yes, putting your units in the calculation matters. I wouldn't take marks off if you didn't, but unit analysis, looking at what happens to your units in the calculation is very important to make sure that you've canceled and rearranged the formula correctly. Okay? So my P1 was 100 kilopascals, my V1 was 30 liters, my P2 was 25 kilopascals, and my V2 was unknown. I leave the unknown as just the variable. That's what I want to solve for. Okay? So when you're rearranging for a certain variable, right now my V2 is multiplied by P2. I want to get V2 by itself. I need to isolate for it. Okay? So what that means I need to do is the opposite. Right now it's being divided by 25. So I need to do the opposite, which is divide by 25 on both sides. What I do to one side of the equation, I have to do to the other side of the equation. Okay? So it cancels here because it's on the top and the bottom of the fraction. And so we're left with V2 equals 100 kilopascals times 30 liters divided by 25 kilopascals. So this is where I'm saying the unit analysis is important. Our kilopascals again cancel because they're on the top and the bottom, and I'm left with liters on the top. You should always be left with the unit you're solving for on the top when you're done the calculation. If you wanted to rearrange the formula first and then put your variables in, right, your formula would be V2 equals P1 times V1 over P2. Then you don't have to move the numbers around. Whichever way you prefer works. So now if I put this into my calculator, so I have 100 times 30 divided by 25. We get an answer of 120 liters. Make sure you always have units with your answer. Now, if I look back at the question to figure out how many significant digits my answer can have, I want to look at all the numbers in the question. There's 3 sig digs there, 3 sig digs there, and 3 sig digs there, which means my answer needs 3 sig digs, which it has. 120 is 3 sig digs. So that, the way it is my final answer. I don't need to round it. I don't need to put it in scientific notation. I just put a box around it, and that is my final answer for B2. Now, the other thing you can do with this is think if it makes sense. My pressure went down, right? It started at 100 and it went down to 25. So that means my volume should have gone up. And in fact, it did. You can also even think about it as my pressure went down by 1/4. So if my pressure is going down by 4, that means my volume should be going up by a factor of 4. Okay, that's what the inverse relationship means. If I take my pressure and cut it in half, my volume will double. So whatever the pressure is being divided by is what the volume is being multiplied by. And you might have questions in your practice or on your test that says, if my pressure is cut in half, what is the volume? So you could, again, just think of the relationship. If pressure is divided by 2, volume is doubled. Or you can say, you can make up your own variables. So let's say pressure 1 is 1. Pressure 2 would then be 2. So if volume 1 is whatever the volume is, then volume 2 you would solve for. Okay, so if it's just a theory question where it's looking at telling you the factor that the pressure or the volume is changing by, you can either just say when pressure divides by 2, I just take my volume and multiply by 2, or make up variables. Okay. All right, I think we have another example, and then that's it for this lesson. The pressure on 2.50 liters of anesthetic gas is 100 kilopascals. So we'll make this V1, and therefore this is P1. If the new volume, V2, is required, 6.25 liters, what pressure must I put this gas under in order to get to that volume? Okay. So my V1 is 2.50 liters. My P1 is 100 kilopascals. V2 is 6.25 liters. And P2 is what we're solving for. Okay? So again, I have P1 V1 equals P2 V2. If I put my variables in, P1 was 100 kilopascals, V1 was 2.50 liters, P2 is unknown, so I'm leaving it as P2, and V2 is 6.25 liters. Now again, I want to isolate for P2, so I need to, right now it's being multiplied by 6.25, so the opposite is to divide by 6.25 on both sides of my equal sign. So it cancels here, and we're left with P2 equals 100 kilopascals times 2.50 liters divided by 6.25 liters. Notice how our liters cancel, and we're left with kilopascals on the top, which again is good because we're solving for pressure. So in my calculator, 100 times 2.50 divided by 6.25, we get an answer of 40. My units are kilopascals, but what about my sig digs? I look back at the question, there's 3, 3, and 3 sig digs in all of my numbers in the question, which means I need 3 sig digs in my answer, and right now I only have 2. So when you need more numbers, you put a decimal and a 0 when you need more digits to your number. Okay, because the answer is 40. I can't make it 400, but I can make it 40.0. Okay, and then that is your final answer with the proper units and rounded to the proper sig digs. Okay, I believe that is the last example in this lesson. So thank you very much for watching this video.